I will talk about the work we did. So for the same topic, but as a part of an interdisciplinary project. So Arne, you're probably familiar with a FOP. It's a vak overschillende project.
Yes.
And this was done. It was undertaken by me, Dr. Pullman, Professor Galvita, with third year bachelor students. So we took this topic and we tried to gain a first idea about how this process could work with the know-how we have. So I will just discuss briefly the content of what we did, and you will immediately notice that it's rather similar to the vision that you have. So I hope that the results that we had from this small project could be useful for you. So
Yes.
it includes a literature survey, the thermodynamic calculations of the materials, and a little bit about material synthesis. How did we synthesize the materials? What did we synthesize? How we characterized the materials? Then we also did some CO2 sorption tests to see if the material works or not. And then we tried to model it from a kinetic perspective. So this is, in general, the areas that we touched upon in this course. So I will start with the literature survey. As you correctly identified, a mine scrubbing is a very common and applied technique for capturing CO2. And I think it will be interesting to know how you approach it and how you determine the limitations of this process. In this literature survey that we did, we know that it's a technology that is very, very mature. It's almost 100 years old now. But we also know that it is, from an exergetic point of view, a bit inefficient, and it works efficiently when the CO2 that has to be captured is in high concentrations in the gas that it has to be captured. So that is a thing that we already know. And apart from that, we also found out that there are other emerging technologies. So on the right-hand side, you see membranes. So membranes are indeed, what they do is they separate the CO2 from other gases. So one molecule, for example, CO2 will pass through the membrane. The other molecule, let's say water or nitrogen, will not be able to pass. So that's how the membrane works. This is more of an emerging technology, but it still is not that mature yet. We also tried to figure out what other people have been doing, and we were quite impressed with a technology that is already now applied on a pilot scale or almost on a commercial scale, and that is for direct air capture. It's not it's very, very recent. So this technology is based on capturing CO2 directly from air with a system that is displayed in this slide. Yeah, so they also have some kind of a filter where the CO2 in the air, which is very dilute, about 400 ppm, as you correctly identified, it is captured by the filter, and you have CO2 free air going out of these big fans, and later you apply a little bit of heat to get the captured CO2 out, and you end up having a concentrated CO2 stream, which you can use for a lot of purposes. It could be for greenhouses, or it could be for making fuels, for chemicals. There are a lot of applications that can take up CO2, but also, as you mentioned, there is also the possibility of just storing it underground permanently. So inspired by something like this, we also thought we could work along similar lines and apply the knowledge that we have in this kind of field from our other works. So what we thought could be an idea would be to use an alkali metal to capture CO2. We have experimental results which show that these alkali metals are very good at capturing CO2. And we also think that it's advantageous to use these kind of metals because they are very cheap and fairly abundant. Yeah, these are everyday materials that we use in our lives. So nothing exotic or unfamiliar here. And the process itself is a cyclic process. So it's very similar to the previous slide that you saw. So basically what we do is we try to capture the very dilute CO2 in the air. That is captured by the alkali metal, which becomes into a carbonate. So that is a compound in itself, and by applying a little bit of heat to this carbonate, we can reverse the process, and we can get CO2 out, and we can have the alkali metal back for capturing more CO2. So it goes in cycles. It's a cyclic process. So to start off with, the students they picked up a few materials. So calcium was one of the materials they picked up, magnesium as well. Then they also picked up potassium, and then a bit of a mixture containing N-doped potassium. So these are the materials that they decided to make. And we also thought it would be very important to look at the thermodynamics. So these are all exothermic reactions. That means that they are favored at low temperatures. Yeah, so the lower the temperature, the more the reaction is favored. What we were interested in is below which temperature can we actually capture CO2 in the air, because CO2 in the air is very, very dilute. So it can be a bit challenging to know at which temperature it's still feasible. And the results that you see here, the T equivalents, they give you an idea about the maximum temperature that you can have for capturing CO2 from air. So if you are at a temperature below this, you can still capture CO2 feasibly. Yeah, it's still feasible to do this from a thermodynamic point of view. So we did this calculation to get a rough idea about which kind of solvent could be good for us. It's very important because it tells you what is possible. Then we tried to characterize the material. So just like you mentioned, we also wanted to use electron microscopy. So this gives us an idea about how the material looks like morphologically from a macroscopic point of view. And you can see the images on the left. So you will see that the silica materials, they are quite, the particle sizes are very, very uniform. So not much variation, because the silica that we used was a very high surface area material, and it was commercially manufactured, so the particles look very similar. On the other hand, if you look at the titania, that has a little bit of variation in the particle sizes. So it's interesting to have a rough idea about how the particles look like. This can be important for industrial applications. And apart from that, we also used energy dispersive X-rays when we were doing the imaging, and this gives us an idea about how much, what is the composition of the material. So we wanted to make 15% calcium oxide supported on silica, and we found out experimentally that actually we had about 14.6% calcium oxide. So it's very close to what we expected. So just as a confirmation, it's very handy to confirm whether the material is what we expect it to be, what we synthesized it to be. So that's why we did this as well. Apart from this, we also did X-ray diffraction. So X-rays are very useful for bulk phase properties, and they immediately give you an idea whether your material is crystalline or not. So if you see the X-ray diffraction patterns on top, the first three, they look very blurry. Yeah? They are not the signal to noise ratio is very, very high. So there is a lot of noise that you see. So that immediately gives you an idea that the material is predominantly amorphous. It's not crystalline. On the other hand, if you look at the diffraction patterns in the lower row, you see that you start to see a lot of sharp peaks. That already gives you an indication that the material is crystalline. So if the material is crystalline, you can understand a lot of other things with such a technique as well. So for example, you can figure out what is the crystallite size. There is not an empirical relationship, but there is a relationship called Scherer equation with which you can have a rough idea about what your crystallite size is. So this technique is useful to understand crystallite sizes that have a size of greater than 3 nanometers. So if your material has sizes of between 3 nanometers to, let's say, 1 micrometer, you can use this technique to figure out what the average crystallite size of your material is. Apart from that, we also did a nitrogen sorption. So basically, this technique tries to absorb nitrogen physically on the surface, and the idea is to cover the entire surface with nitrogen molecules. And by doing this, we have an idea about what the total surface area of the material could be. And this technique is also useful for other textural properties. For example, with this technique, you can also figure out what is the pore volume. So how much void volume can you have in the pores of your material? So that's also very interesting for different purposes. The more pore volume you have, the more voidage you have for your gases to go into the material. So that makes it quite interesting. Apart from that, you can also figure out the pore size distribution, especially in the mesoporous range. So between 2 nanometers to, let's say, 50 nanometers, you can have an idea about what your pore size distribution in your material is. CO2 is a very small molecule, so if you have pores between 10 nanometers, there is no problem for CO2 to go into your material. But you can confirm this by let's say Ny-sorption, and the students applied this technique on their materials, and they found the values that are listed here in this table. So they started off with a very, very high surface area material, and then they loaded different alkali metals on top of these materials. And what you see is that the support itself had a very high surface area, but after the active material was impregnated on the support, the surface area decreased as well. So it means that some of the pores were blocked when the active material was loaded onto the support. But nevertheless, these numbers are very, very big numbers. Yeah, so to have 157 meters square per gram, it's a huge quantity. So just to give it a perspective, a typical cot that students live in has a surface area of about 20 meters square. But this surface area says that just 1 gram of your material has a surface area of about 200 to 300 meters square. So that's really huge in a very, very small amount of material. And this surface area is quite useful for having a reaction. So the more surface you have, the better chances you have of initiating a reaction or giving enough possibilities for the surface to have a reaction with a gas phase or any other phase. Apart from that, we also did some tests to figure out if our materials are indeed active for CO2 capture and release, and we did these tests on AutoChem. So I see that you're already familiar with it, and you're also familiar with the pulse chemisorption. So what we did was also pulse chemisorption. So first, we pre-treated our material. Can you see my cursor or not? Okay, maybe now you can see it. So this setup that you see here, it's good for programming and automating your experiments. So what we did was we first pre-treated our materials to make sure that there is no CO2 captured by the material, and after that we started sending pulses of CO2 so that the CO2 starts to react with the surface and stick on the surface, so to speak. And later we increase the temperature to see that to check if we can actually release the captured CO2. So this was our program, and it's possible to automate it using this setup here. And where exactly do you place your material? You place it inside this U-tube reactor. So this is where your material is. You can measure the temperature with this thermocouple, and then you can start this program. The good results that we saw was that it was possible to capture CO2 on some of our materials, and during this regeneration step, we could actually see that we have a peak at about 110 degrees centigrade. So that was a promising result. And apart from that, we also checked out how much of the CO2 could we capture in when we put these 20 or so pulses. So we saw that our magnesium oxide material could capture the most CO2. It was about 30%. And we could start to release CO2 at about 80 degrees centigrade, which is quite good, I would say. The other materials that you see at the bottom, the potassium and the nitrogen potassium, the experiments were done by adding a bit of water, because these materials need water as well to capture CO2. So that's why their capacity is about 100%. So it's different from the materials that you see here. But among the first three materials, magnesium oxide seems to be quite interesting, so to speak. So after doing these tests, we also thought we could try to model the capture and the desorption characteristics of CO2. We've mainly focused on the regeneration, so to release CO2. And we did experiments at different temperatures and different CO2 concentrations, and the students found out that their activation energies are fairly low. So this gives us an idea about what kind of phenomena is occurring. So typically for chemisorption processes, you have an activation energy of about at least 80 kilojoules per mole, and for typical physisorption processes, you have activation energies less than 30 kilojoules per mole. So what the students found out that the activation energies that they calculated were in the physisorption regime. So that also gives some insight about what was going on during these experiments, how the CO2 was captured and how it was released. So that I think brings me to the end of the work, or end of the summary of the work that they did.